Welcome back, and today is the fourth lecture. Here in today's lecture we are going to talk about model development for MATLAB simulation. So, the topics covered in today's lecture are modeling of a series RLC circuit and block diagram for simulation. Then modeling of series parallel RLC circuit along with some parasitic. That means, initially we will consider ideal series parallel circuit, then we will consider practical parallel circuit with parasitics. Modeling of parallel RLC circuit with parasitic component, then modeling of conventional and synchronous buck converter, that means DC-DC converter that we have discussed in the previous lecture, and we want to build model for MATLAB simulation, and then modeling of a boost converter and model generalization. So, the series RLC circuit is a very simple well known circuit, and it is shown here. Here we are considering one input voltage V in, which can be DC voltage, which can be pulsating voltage, which can be AC voltage. It is just a source, and the voltage across inductor is VL, which is shown here, and voltage across resistance is VR, and with their polarity shown here. And because of the series circuit here, the inductor, the current IL is common for both inductive element as well as the resistive element. So, we can write the voltages equation of the voltages like a VL, which is the inductive voltage, which is V in minus VR, where VR is nothing but the drop across the resistance, and we can write now VL, which is V in minus ILR. Now, these are the equation of voltages, and since it has one storing element, so naturally it will have dynamics and it will have a first order. It is a first order system. That means a first order differential equation, which is L di dt dIL dt, that is nothing but the VL voltage across inductor, that is nothing but input voltage minus voltage drop across resistance. Now, we want to implement in the building block, and this implementation is quite similar to what we will be doing in MATLAB Simulink, the implementation in using MATLAB Simulink. So, the voltage VR, since we are using a resistance, and this resistance is like a constant block, and the constant multiplied by current will be the voltage. And when we will implement in Simulink, we will use this symbol R rather than putting a value, so that all these parameters that we are plugging to the Simulink model, we can define separately using a .m file in the MATLAB, that we will discuss. And then once we set this parameter value, then we can actually run the Simulink model, and accordingly we can simulate the AD circuit. Now, we know the voltage across inductor V in minus VR, it can be used using a summing block, it can be realized, and that is also available in MATLAB. So, all these building blocks are designed keeping in mind the available blocks in Simulink. Now, again the dynamics. So, dynamics means dIL dt, it is 1 by L into this is your VL. This is my inductor, voltage across inductor, which is nothing but V in minus IL into R. So, if we want to plug in this block, it is like a feedback block, where this is our dIL dt, and if we integrate, then we will get inductor current, and here we can set the initial condition of the inductor current. Again, if we plug in, if we go inside the block, whenever we will simulate in MATLAB Simulink, we will open this block, we can write symbolically IL0, and we can define this IL0 at the beginning using a .m file, so that we do not have to change manually each and every initial condition, that will be even confusing. Then this is a load resistance, this is the inductance voltage, which is nothing but inductance voltage into 1 by L, this is your dIL dt, and this is implemented here. Now, going for the series RLC circuit. In the series RLC circuit, all inductor, resistance, capacitors are connected in series. We can take output either across capacitor, we can take output across resistance, but this RLC circuit is in a series combination and it is supplied by a source V in. For this series circuit, the inductor current IL or this series current IL is common through inductance, capacitance and resistance, and I have denoted the voltage across individual element like for inductor VL, for resistance VR and for capacitor VC. Okay. Now, dynamics of this system. So, we have two energy storing element, one is resistance, another is the capacitance. So, these two are the energy storing element. So, we can expect for each energy storing element there will be one first order equation. The overall system can be a coupled second order equation or two decoupled first order equation depending upon how we are writing. I mean, of course, they will not be decoupled, but we can write either two first order equation in this format like in state space, or you can write completely using a second order differential equation. So, the first part we are talking about inductance, the dynamics of the inductor current or basically the current going through inductance. In this case, it is the series current. So, dIL dt is 1 by L, that is the, and this part is our VL, this part is our inductance voltage. So, dIL dt is equal to 1 by L multiplied by what is VL? It is nothing but V input voltage minus the drop across the resistance minus the capacitor voltage. And what is the equation of the capacitor voltage? It is dVc dt, it is nothing but IC by C, IC is the capacitor current, C is the capacitor's value, capacitance value. In this case, the capacitor current is same as the inductor current. So, it is simply IC into IL. Now, the dynamics we are writing dVc dt equal to IC into IL, that can be implemented by this block where 1 by C is the constant, where we can plug in the capacitance value, and in the Simulink when we will implement we will use a parameter C, so that we can define the parameter value in the .m file. Similarly, we can define the initial condition of the capacitor voltage in this inside this integrator. This is an integrator. Inside the integrator, we can plug in the symbolically we can plug in Vc0 and we can define outside. If we consider inductor current dynamics, then we can actually draw the block diagram, because the resistance is constant and it has 1 by L, which is nothing but it is shown here, you can see it is here, and this resistance is shown here, okay. And we can implement the whole circuit, and this is our capacitor voltage, this is our input voltage, and this is our inductor current, and here we can actually again set the initial value of the inductor current. All right. Next part, the series RLC circuit, whatever we have shown, the implementation of two separate like a dIL dt and dVc dt. We got IL and Vc. Once we got it, then we have to replace this Vc with, I mean, we are getting Vc from here and that we have to replace here. We are getting IL here and we have to replace IL here. So, in the next block we are going to merge together. So, one dynamics we have inductor current, I mean capacitor voltage that is coming out from here, another we are getting inductor current, and we need to combine to get the complete circuit. So, this complete circuit, since it is linked with the inductor current, we can set inductor current initial value here, and it is linked with the capacitor voltage. So, we can link capacitor voltage here, initial condition, and this shows the complete circuit where you can get inductor current out and capacitor voltage output. That means, we can, if we want to simulate this circuit, we can show the profile of the inductor current for a given input voltage profile, and you can also show the capacitor voltage profile. If you want to show the resistance voltage across the resistance, you can tap this point, we can show the voltage across the inductance from this point. So, we can see different waveform, different voltage and current waveform, we can tap from different points. Now, we want to move to parallel RLC circuit. In the parallel RLC circuit, here we are considering the capacitor and the resistance are in parallel, and here we may consider this resistance to be a load resistance, where it can change, the load resistance can change. I mean, this is just a circuit, we can use it in different purpose. But unlike in the series circuit, the current passing through resistance and capacitance, they are different from the series current IL. So, now we have to, that is why we have defined individual current like IL is the current going through the inductor, IC is the current going through the capacitor, and I0 is the current going through the resistance, the load resistance. And we are specifically showing the current IC which is going in, and it is going inside, and it is going into the capacitor through the positive terminal. So, this current direction is used for charging the capacitor, I mean the notation is used for that purpose. So, we can write the inductor current dynamics dIL dt like we already know, it is VL by L, and in this case VL is nothing but the voltage across inductor is input voltage minus this load voltage. That means, we are talking about the voltage across this. So, left side is the input voltage and the right side is the output voltage. So, here Vc and V0 are same. So, here V0 is equal to Vc in this case. So, they are same. So, you can use either Vc or V0, does not matter. Similarly, you can write the differential equation corresponding to the capacitor voltage, and what we will get dVc dt is, this is my IC, this is my IC. So, it is already shown here. So, I can erase this part. Okay. So, this is my IC, yeah, this is my IC, by C is my rate of change of capacitor voltage, and IC is nothing but IL, this current minus load current, that is your IC. And as I said, V0 equal to Vc here, and what is I0? Since it is a resistive path, I0 is nothing but V0 by R. Now, this shows the complete dynamics, because we know how to plug in this equation, we saw in the previous example, we know how to plug in this block in the previous example. So, this block corresponding to implementation of the inductor dynamics, this is linked with the capacitor dynamics, and then we can combine together to get the complete block. Here we can set IL0, the initial current, and here we can set the Vc0 is the initial value of the capacitor. So, we can implement parallel RLC circuit using Simulink, using this block diagram representation. Now, whatever we discuss, we have used ideal inductance, capacitance and resistive component. But now, we want to consider practical parasitic. For example, if you take an ideal inductor, the inductor will have some terminal lead where there will be parasitic resistance. So, that means we need to consider the resistance of the inductor, and this resistance will have effect at low frequency, like particularly for DC. Similarly, inductance, when we connect in a circuit, it has two pin like a two if we use a SMD inductor or a through hole inductor, like a through hole, we are soldering between 2 points. So, these 2 points soldering point can behave like a two conducting plate, and where air is the dielectric. So, it can also have parasitic capacitance effect. Similarly, if we consider capacitance, an ideal capacitance will have, in a practical capacitance is not an ideal one. That means, it will also have some leakage effect, and leakage effect means if you keep the capacitor for long time, there will be self discharge. I mean, it will discharge by itself and the process can be very slow. In order to emulate this discharge process, we can connect a parallel resistance with a large resistance value, so that that process of discharge is very slow. So, we can consider a parallel resistance. Also, the capacitor lead where we connect in the circuit, that will have parasitic resistance, that will have like a trace resistance, that will also have trace inductance. So, if you connect all these parasitic, then we can actually write in terms of impedance form. After simplification of the real part and imaginary part, it turns out to be all this real part can be clubbed together to get what is called equivalent series resistance, which is RC, and we sometimes call it as it is known as ESR, equivalent series resistance of the capacitor. It is not a physical resistance, it is not a pure resistance, because this resistance is a equivalent resistance, which is also function of frequency. Because if we actually start from the basic practical capacitor, as I told, if you consider the leakage resistance, parasitic inductance like a trace inductance, trace resistance, and if you write the whole complex equation, and if you separate out the real part which is represented by RC, there will be a frequency dependent term, and it also depends on that resistance also depends on the trace inductance, trace resistance. So, many other factors. This ESR also depends on temperature. That means, if the capacitance is operated at different ambient temperature, this resistance can also vary, but we generally write as an equivalent resistance, which is equivalent series resistance. Similarly, for the inductor, as I said, we can have a parasitic resistance which can be a trace resistance, and this is also called in many cases is called DCR, DC equivalent resistance, and that is denoted as RL of the inductor, DCR. Now, we still have two energy storing element, inductor and capacitor, the ideal part of the practical inductor, and we can write DIL dt, the current, the rate of change of current through the inductor, which is again 1 by L into VL. VL is the voltage across inductor. I am talking about this voltage, and this voltage, what will be this voltage? This voltage is V in, like this voltage, minus this drop across this resistance, minus the terminal voltage, which is V0. That means, we are talking about V0, this terminal voltage. So, this represents VL, and we can implement this circuit because you already know how to plug in this first order differential equation, and here we can set the initial value of the inductor current. We want to now realize the dynamics of the capacitor, and here we are talking about the voltage across the ideal counterpart of the capacitor, of the practical capacitor, and this derivative of the voltage dVc dt is 1 by C into IC, which is nothing but, this is my IC, which is nothing but in this case IL, this current is IL and this current is I0, and this capacitor current is IL minus I0. So, we can also plug in this equation into block diagram, and here we can set the initial voltage of the capacitor. Okay. So, we have implemented the dynamics separately, the inductor current dynamics as well as the capacitor voltage dynamics. Now, we need to get the block diagram of the complete parallel RLC circuit with parasitic component. So, voltage across resistance is not, in this case, is not equal to the capacitor voltage, because we have another voltage coming in, that is the voltage across this path. And what is this? This is nothing but RC into IC. So, this drop will also be there. So, this is the component plus Vc, which is the capacitor voltage, and the sum is the output voltage. But the capacitor current is still remains, that it is the subtraction of the inductor current minus load current, and the load current which is going to the load resistance. In this case, this is a load resistance. So, if we use a resistive load, then we can get the current simply by dividing output voltage by resistance, that means V 0 by R. Now, it is not necessary the load has to be always resistive. We can consider a combined load consisting of a resistive load plus constant current load. Even we can consider constant power load. So, different type of loads are possible. So, we need to accordingly get the load current, how is it a function of output voltage. In case of a constant load current, we can simply use a constant value. That means, we can replace the resistance with a current sink, because it is going out. In case of a constant power load, the I 0 will be power magnitude by V 0. So, because the product of I 0 into V 0 is P 0, constant power, which is constant. So, by that way we can consider different type of load, and the complete block diagram is shown here. That means, we know this block is corresponding to inductor, and this is the initial value of the inductor current. This will correspond to the initial value of the capacitor voltage, and by this block we can get very easily the output voltage, inductor current, capacitor voltage, everything we can get. Even if we want to tap the capacitor current, we can simply take from this point, this current, and capacitor current multiplied by RC is my V 0. Similarly, I 0 we are getting V 0 multiplied by 1 by R, because voltage by resistance is the current. So, if we want to consider the load current with the combination of resistive load and current load, so you can put a adder block also here. We can put a adder block here, the current due to the resistive load, plus we can put another constant current load like that. So, these are all possible, so that the net load current which is going out of the the current like a RL branch is it consists of resistance, other thing. But here, since we are talking about parallel RLC circuit, so it is a purely there is no constant current load in this case, but whenever we will show converter, there the load need not to be always resistive load. Okay. Now, we learn about parallel RLC circuit with practical parasitic, and I will show you how nicely we can connect this with the switching converter. If we take a buck converter, you will see this RLC branch will look like a parallel RLC branch, which was there in the earlier example we saw, and this all RLC, particularly L and C, we can replace with their practical parasitic. And the switches in this case, actually these switches are not ideal switches. So, this is I am just showing a simulation result, where this is an ideal switch, and it shows the Q. When the Q is 1, the current rises, because I am talking about this particular path, the Q is 1, and again it goes like this. So, this is my Q. When the Q is on, the switch is on. When the Q is 0, the switch is off. Okay. So, you can accordingly draw the waveform. Okay. Now, This switches, there is this is called synchronous buck converter, since we are using two MOSFET and they operate in a complementary fashion that we discussed earlier. That means we can achieve negative current, because MOSFET also allow the current in the other direction. So, this converter always operate in continuous conduction mode, even under no load condition. If the load resistance is removed, it will still operate. In that case, there will be back and forth power flow. That means, when the current is positive, the current will come out from the source. When the current is negative, that means you are giving the charge back to the source. So, inductor current can be negative under light load condition. So, in this synchronous buck converter, if we want to replace all these components including switches with their practical parasitic, we already know about this RL, RC, but now for switches we are considering ideal switching. That means, we are not considering here turn on turn off practical process, but that can also be included if we can include the switch models. But here we are only considering the DC resistance, on time resistance of the MOSFET. R1 and R2 are the on time resistance of switch S and S bar. And if you consider Vx, that means, if you just look at this circuit, you see for this RLC parallel circuit we already have implemented the block diagram. Only difference, in the earlier circuit we have a input voltage V in, but now here voltage is Vx, and in this case this voltage is called switch node voltage. This voltage is not a fixed voltage, it is a pulsating voltage. So, we can again write all the differential equation. This is our VL, the inductor current dynamics, we can write capacitor voltage dynamics, we know the capacitor current, but here instead of input voltage, now you have a switch node voltage. So, this voltage is switch node voltage, and this is, we call it as a switch node voltage, switch node voltage, but this voltage is a pulsating voltage. When Q is on 1, that means switch is on, it takes V in minus RL, sorry, V in minus R1 into IL, because the drop, this represents the drop across this resistance. When the switch is off, that means S bar is on, then it takes minus R2 into IL, that means the drop across this part, and 1 minus Q means when Q is 1, this part does not come, does not arise. When the Q is 0, then this part arises. So, depending upon the Q configuration. So, it is a pulsating voltage. So, now again we can write down this equation, and we can, this part we already know how to implement, and we can plug in this IL initial condition. We can also plug in the capacitor voltage, there is no problem, we already did it, but these parts are well known, we have already shown. But what is interesting here, we need to derive the switch node voltage. So, this switch node voltage, when the Q is on, this is V in minus IL R1, that means we are talking about this part of this circuit. When the switch is off, we are talking about this part of this circuit, this part is disconnected. So, it will be minus IL R2. So, we can plug in this and we can simulate using a switch in the MATLAB Simulink, and this switch represents when Q is 1, it will take the first input, input 1, this is the first input. When Q is 0, it will take the second input, which is minus R2 into IL, and that is why by that way we can generate the switch node voltage. Now, we can combine this whole thing to get the complete representation of the synchronous buck converter. This whole part is well known to us, because we did it for our parallel RLC circuit with parasitic. This is a new additional block which is coming due to the switching configuration of the switch node voltage, because it is not a fixed voltage. This is, you can think that in a parallel RLC circuit we can also apply a pulsating voltage. So, similarly we are generating the pulsating voltage from here. But now, if we consider a conventional buck converter where the low side MOSFET is replaced by a diode. Now, this is the diode, we have replaced the low side MOSFET. If we want to represent this circuit using their practical parasitic, that means real component, then this MOSFET, actually this should be an ideal switch, this will become an ideal switch, and it is basically a single pole single throw switch with a series resistance of R1, that is the on time resistance. The diode will be replaced by this is an ideal diode, this is an ideal one, this is an ideal one, along with the practical parasitic. What are the parasitic in a diode? We can consider the resistance of the diode like a RD, resistance drop, series resistance of the diode, or it is called forward resistance, and also the forward voltage drop, which is VD here. Now, like similar to the earlier, we can also denote this as a switch node voltage. This is my switch node voltage, switch node voltage. Okay. What is the difference in this case compared to earlier? Earlier case, it was low side, we have a MOSFET which can carry current in the negative direction, but now we have diode. So, diode cannot carry current in the negative direction. So, whenever the inductor current becomes 0 or it try to go negative direction, then this part during the off time, because when the switch is off, I am talking about the scenario when the switch is off, the current is falling. When the current hit the 0 current, then the diode is reverse biased, so it cannot carry current. In that case, the voltage across inductance, or basically DILDT, rate of change of current should be 0 and current also is 0. So, now DILDT earlier was a single equation which was this one, but now we have an additional logic due to the 0 current of the diode. So, we can again write the capacitor equation, we can write output voltage equation, we can write the switch node voltage equation, all this we can write. So, we can derive the switch node voltage, and along with that, so this is somewhat similar to the earlier synchronous buck converter, only addition is that you have a diode forward voltage drop, and the resistance of the forward resistance of the diode you can think like analogous to the on resistance of the MOSFET. But due to this 0 current logic, which is the discontinuous conduction mode, we need to do a little bit different thing. That means, we know when the switch is on, this is a condition, when the switch is off, this is a condition, and along with diode reverse, this is without 0 current, this is a straightforward when the current is positive, this is simply enough, and we already have this for the synchronous buck converter, only we are adding this particular block. But what happens when this 0 current logic comes in? So, how can you realize? So, you can realize, you can see we are generating a QD block which corresponds to a switching signal when the DCM condition is hit, that means 0 current is hit. So, this signal is used when QD equal to 1, that means the DCM logic is hit, then the VL, the voltage across inductor is 0. If the voltage across inductor is 0, DILDT is 0. So, whenever it hits 0 current, we are keeping the derivative of the inductor current 0. As a result, inductor current is 0 and its derivative is 0. So, it will remain at 0. When the QD is 0, that means off, it takes the earlier value, that means this one, this is the value, and this is a realization. So, this can be realized by a DCM enable active high, where you say this block actually detect the 0 current using a comparator. So, if the inductor current is compared with the 0 current, and whenever inductor current try to go below 0 current, then this comparator output becomes high. If the comparator output becomes high, that means I am talking about the IL is less than equal to 0, this gives rise to QC equal to 1. when QC equal to 1, this signal is high. Now, and we are talking about the scenario when output the Q switch is off. That means, if we do this thing like a current is already at 0 and switch is turned on, then if we continue this logic, the inductor current can never rise. So, in order to avoid that, we are talking about, we are also checking the status of the switch, that means the control switch of the high side MOSFET. If that switch is 0, that means that switch is off, that means diode is carrying. We are talking about the turn off condition. If it is in the turn off condition, this logic is also 1. Now, we are giving an additional enable logic. Do you really want DCM to be enabled or not? If DCM is not enabled, then as it is like a synchronous buck converter, there is no discontinuous conduction mode. This block is particularly used because in general, integrated circuit, instead of using a pure diode, they use a MOSFET in the low side, and they also use an emulated diode, that they emulate a diode using transistor. So, whenever you want to achieve fast step down transient, that we will discuss later, we allow the current to go to negative direction for some time, so that the capacitor can be quickly discharged, and then when the current again comes close to 0, then we enable the DCM operation. So, by that way this Q DCM can be configured in the run time. Okay. If Q DCM is set to 1, then only DCM operation is possible. But if it is set to 0, if Q DCM is set to 0, whatever DCM condition is detected, you will not enable a DCM operation. That means, it is now we are using a MOSFET. Okay. So, with this block, how can we generate this Q DCM? QD. Now, so this block is generating QD, which is used for this purpose. That means, when the QD is 1, that means the DCM is detected and it is enabled, then DIL dt will be 0 and inductor will remain at 0 current. When this block will be 0, then it will take the regular operation when the inductor current will rise or fall depending upon the switch condition. This is particularly when the current is above 0. So, now we can implement the complete buck converter circuit, including this DCM enable block, and this model can be generalized. That means, if we set Q DCM to be 0, then as if we do not want a conventional buck converter, this can be configured to a synchronous buck converter, where we can simply set the diode drop to be 0, and this RD is now replaced with the off time like on time resistance of the low side MOSFET. So, now this can be a synchronous buck converter can be derived, or the model can be implemented using conventional one by setting this parameter. So, the load current can be directly used as a load current, or it can be resistive load, it can be constant current load, it can be constant power load. Accordingly, the load current should be generated using a block. Now, if you take a generic form of a boost converter, so boost converter inductor is sitting here, and again we have a switch node voltage. This is my switch node voltage, and again we can consider the diode drop. If you consider a conventional boost converter, ESR of the capacitor, DCR of the resistance, we can write the derivative of the inductor current. Again, if we enable DCM operation, we need to check whether inductor current is going below 0, then we need to stop the current, or need to keep the current at 0 condition. Again, this block can be realized the similar way like a discontinuous signal, that means this QD, and the QD can be generated by a DCM enable clock that we discussed earlier. Now, the boost converter dynamical equation, the output voltage, the capacitor voltage can be realized. That means, you can see the capacitor current for the boost converter here. It actually becomes, whenever the switch S is on, that means Q is high, then inductor current actually flows through this path, and the capacitor current is nothing but minus load current, and this can be shown from here. But when the switch is off, then it is going to this path. In that case, the capacitor current is nothing but inductor current minus load current. So, you can write in terms of a switching signal 1 minus Q. Okay. Then output voltage is nothing but capacitor voltage plus the drop across this ESR drop, and which is nothing but this drop. So, you can implement the output voltage equation, and here we have to consider the capacitor current is discontinuous, and that can be realized by putting a switch block. When the switch is on, it will take 0 current, that means IL equal to 0. When the switch is on, for Q equal to not IL equal to 0, I will say sorry, this current, this is not IL, that means this current is 0, this current, this particular current, let us say I dash, it is 0 when switch is on. When the switch is off, it is nothing but the inductor current. So, the complete diagram of the inductor boost converter, the switch node voltage which is equal to IL into R1 when the Q1 is on, and this is equal to VDD plus IL RD plus V0 from looking at this terminal, this side, we are talking about this side, when the switch is off. So, you can plug in this switch node voltage, and that can be realized using this switch block in the simulink. So, that means we can now implement the boost converter. Again, if we do not want a DCM operation, that means if we do not, instead of a diode, if we replace with a switch synchronous boost, then we can disable the DCM operation also using QDCM block that we discussed earlier. That means we can what we discussed earlier, the QDCM block we can set to 0, and this we will show in the MATLAB simulation how to enable and disable DCM operation. In summary, we have discussed model development for simulation, and these models are versatile for reconfiguration. In fact, we can plug and play type blocks. We can, if we want to implement multiple converter, we can plug on this block, we can create subsystem. If we want to realize more complex converter consisting of more energy storing element, we know how to implement individual storing element differential equation into the Simulink block, then we can simply keep on adding this block. The MATLAB Simulink is sufficient. We do not need a specific like a specialized toolbox like a SimPower system and other toolbox. So, these custom blocks enable you to better understand the converter, and you can realize many effects in Simulink block itself. And we can sync the MATLAB code with the Simulink file, and that the design, we can simulate design oriented case study, and these blocks are plug and play, and there are modularity, like we can make the design modular, and MATLAB demonstration to be shown in the next presentation. Thank you very much for today.